Welcome to the Predictive Maintenance demo. In this segment, we will focus on field-level support of equipment assets. In terms of a value proposition, we will be looking at extending asset life, preventing asset failures, decreasing labor and MRO inventory carrying costs. The scenario is our company has manufactured electric motors. We want to support these motors in the field, and we have captured the following data: equipment ID, days in service, and a number of condition monitoring data points, such as operating voltage, amperage, temperature, as well as the month that the motor was manufactured, its service history, and any costs associated with planned and unplanned maintenance. There are three part failure modes: failures relating to capacitors, bearings, and the motor shaft. We will be using predictive analytics, including Weibull analysis and predictive models, such as neural networks and logistic regression. These models will allow us to do a number of things. First, it will allow us to do automated root cause analysis on failures. Second, it will allow us to determine the reliability of each motor that is in service under any set of operating conditions at any point in the future. Let's take a look at how we can use the Cognos BI interface to better understand and visualize the output of the SPSS predictive analytics. Let's start by looking at the predicted field failures for our motors. As you can see from this pie chart, most of the predicted failures will be capacitor failures, followed by bearing and shaft failures. But what's really nice here is that the SPSS predictive analytics have told us the specific set of operating conditions, manufacturing conditions, and also information about the days in service and maintenance schedule that is leading to failures. Let's drill down on our capacitor failures. What you find is the first group of failures, 285 of the units out of the 100% of these 285 units are predicted to fail if they've been in service for more than 394 days. So clearly this is a normal wear out, and we probably need to address these units, but it gives us a very clear rule for predicting failure. The second rule is a little more interesting in that it's related to the month of manufacture. So it's February of 2008 to May of 2008, and if the operating temperature is between about 78 and 82 degrees, we have a very high likelihood of failure. Again, this is pointing us to manufacturing issues with quality. It's also pointing us to groups that are likely to fail so that we can be more proactive about managing these assets. We can also look at a dashboard of all the units that are in service over the next 90 days and look at units that are likely to fail and determine which units are not going to have maintenance to prevent that failure. As you can see in this first bucket of 1 to 7 days, we have a large number, 95 units, of motors that are likely to fail, and none of them are actually scheduled for maintenance. Let's actually drill down and take a look at one of these units. So let's look at motor 2058. And motor 2058, we want to look at its reliability over time and look at when it's set up for planned maintenance. So here we have on the horizontal axis, the days in the future, and then we have the failure probability or likelihood on the vertical axis. As you can see, this unit has a number of issues going on. We have a bearing failure that actually by the time of the maintenance is actually on a decline, but never really gets above 20%. Whereas we have a shaft failure that's fairly high at 35%. And then what's more interesting is this capacitor failure, which has a very steep ramp up in failure probability very early on, and it's well before the scheduled maintenance. So as you can see, if we can move the scheduled maintenance back, we may very likely prevent a failure of this motor. The converse of this would be places where we are performing maintenance way too early, well before any predicted failure. So if we look at motor 1688 here, again, we'll look at a similar chart. The difference here is that we've identified a motor that has a very low failure probability for the next 80 days. However, we're scheduling maintenance 12 days out. So as you can see, we could delay this maintenance by at least 30 to 45 days and still not have any increase in failure. And we can reallocate those resources to the prior case, which would be one where we actually need to move the maintenance schedule up. So understanding the reliability of each piece of equipment and knowing which component is likely to fail greatly helps us reallocate our maintenance resources to proactively manage our assets. Let's take a look at the SPSS analytics that are driving this solution. We'll start with Weibull analysis, which will help us explore our data and better understand the failure modes we're experiencing. So we have experienced three types of failures: capacitor failures, shaft failures, and bearing failures. Through Weibull, we can better understand what the failure mode is for each of these three equipment types. When we ran the capacitors, we realized that the slope was 2.2. This slope implies that we are seeing normal wear-out failure. Shafts likewise have a slope of 4.2, which again implies a normal failure, wear-out failure. Whereas when we look at the bearings, we see that our slope is 0.92, less than 1, which would imply that we have infant mortality. Traditionally, this is usually related to a quality issue. So let's go ahead and take a look at the bearing failures a little closer. We're going to use a decision tree to generate a rule set that will identify the root cause of this infant mortality. So the first thing I want to show is that by generating this model to predict which bearings were likely to actually have the issue of infant mortality, we're able to generate a highly accurate model. So it's over 94% accurate for both the testing and training data sets. So we can feel pretty confident in the results of this root cause analysis. So as we drill down into the actual decision tree and look at the rule set, we see there are 4 rules for these failures. And what we find out is that these early failures are related to operating temperature, operating amperage, and operating voltage. The bar chart here shows us the failures and the variables that are important in what drove those failures. So the most important variable in terms of driving this infant mortality would be days in service, the days from last service, the operating amperage, and the operating temperature. So the beauty of this approach is that the process of performing root cause analysis is fully automated. So from Weibull, we were better able to understand the nature of our failures. We had 1 case of infant mortality with the bearings and 2 cases of normal wear out. You can also use Weibull to actually calculate the reliability of equipment assets in the future. The problem with this approach is that it only includes time as a variable and does not include condition monitoring data. So therefore, if amperage and voltage were a driving factor in reliability, Weibull would not be able to include them in its analysis. Weibull does, though, allow you to calculate the mean time to failure, which is an important measure of reliability, and in this case it was 263 days. Let's move on and look at the predictive modeling approach to modeling reliability. And again, we have our capacitors, our shafts, and our bearings. And if we look at our data set, we see that we have information about the equipment. We have what type of failure we have experienced, if we have experienced one, how many days it's been in service, condition monitoring data such as the operating voltage, amperage, and temperature, the month that the motor was manufactured, and then its service history. We take this data and split it into two data sets, one for training the model and one for testing the model. In this example, we're actually using a Bayesian network. And if we run our model against our test data and look at its overall accuracy, we see that we create a fairly accurate model, more than 70% accurate in being able to predict failures. We can calculate the mean time to failure, and the mean time to failure was 266 days, again in near perfect agreement with what we learned from Weibull. And we can actually learn more about what is driving failures. So in this particular example, we can see the linkages between variables. We can also see how important they are. So when it comes to capacitor failures, days in service is the most important. But what's interesting here is that the month that it was manufactured is the second most important, which means that we have apparently had some quality issues and variable quality over the months of manufacture. Service record also plays an important role in reliability. For the shaft failures, we use logistic regression. And the shaft failures are almost completely and entirely driven by days in service. So that, as we saw in the Weibull, this is a normal wear out. So you would expect that the days in service would be a primary driver. Bearing failures, we used a neural network. And again, days of service is very important. And then the service history being the second most important, and then third being the month of manufacture. Again, with the neural networks, we're able to create a nearly 80% accurate model and being able to predict equipment failures. Now that we have built these models, which can leverage both the equipment history of when it was manufactured and also its condition monitoring data, we can now build a deployment that will allow us to generate estimations of reliability over the next 90, 180, 365 days, whatever period we choose. We can look at how likely capacitor failures are, shaft failures, and bearing failures are. And we can do a number of different things. We can look at the reliability of a specific motor. So here you see the day increment starting at current day, what is the reliability? And if we scroll over, we can see what the probability of a capacitor failure is, a shaft failure, or a bearing failure. As you can see right now, we have a very high bearing failure probability. So this is something we should probably be looking at in terms of a maintenance schedule. And then over the next 90 days, we can calculate those failure probabilities. We can also look at how many failures would we prevent if we did predictive maintenance, if we use the models to help us understand what the reliability is, and used a maintenance schedule that matched that reliability estimation. So out of the 1,100 total failures, we could prevent 102 by having a more proactive maintenance schedule based on predicted reliability rather than a shotgun approach. Finally, we can take this data and export it for use in our dashboarding and to better align our maintenance schedules with the actual reliability